Welcome again to this session, which is a continuation of the previous one on sections 16.1, 16.2, and 16.3. So the purpose of this part is to have one complete example. So in this example, we have a motor shown here in this photo used to turn a wheel and attached blower. Right here, that's the blower, that's the wheel. Now, if the pulley right there, A, connected to the motor begins to rotate from rest with a constant angular acceleration alpha A, which is 2 radians per second square, we would like to determine the magnitude of the velocity and acceleration of point P on the wheel after the pulley has turned 2 revolutions, assuming that the transmission belt, which is right here, does not slip on the pulley and the wheel. So let's start by converting the revolutions of pulley A into radians. So we have theta A, which is equal to 2 revolutions multiplied by 2 pi radians per 1 revolution, and this is going to give us 12.57 radians. Now, since alpha, which is right there, is constant, then we can use the constant acceleration relations. So we can take, for example, clockwise as positive, and we have omega square equals to omega 0 square plus 2 alpha c multiplied by theta minus theta 0. So here we have omega A square is equal to 0, since it's starting from the rest, plus 2 multiplied by the acceleration, which is 2 radians per second square, multiplied by the angular position, which is theta, and it is a 12.57. We just calculated it, minus 0. So how much is this going to give us? Omega A is equal to 7.09 radian per second. Now, from the gears relation, which is V equals to omega A RA, which is equal to omega B RB, we can have 7.09 multiplied by 0.15. That's the angular velocity of A, which is the pulley, multiplied by its radius 0.15, which is equal to omega B multiplied by 0.4. That's for the wheel. So we can find omega B, which is equal to 2.659 radian per second. We can also find the acceleration, which is the tangential acceleration, AT, and this is going to be equals to alpha A RA, which is equal to alpha B RB. So if we substitute, we have 2 radians per second square multiplied by 0.15, which is equal to alpha B multiplied by 0.4, the radius of the wheel. So we get alpha B, which is equal to 0.75 radian per second square. So to study the kinematics of point P, as shown in this diagram, we have its velocity tangent to the path, which is circular, and we have the tangential acceleration and the normal acceleration. Just don't forget that the wheel here is called B. So the velocity P is indeed equals to the angular velocity of B multiplied by its radius, which is RB. This is equal to 2.659 multiplied by 0.4, which is going to give 1.06 meter per second. Now, AP, the tangential component, is equal to alpha B RB, which is equal to 0.75 radian per second squared multiplied by 0.4. This is going to give you 0.3 meters per second square. Lastly, we have AP in the normal direction, which is the omega B squared RB. So this is this is, let me clear it up, sorry about this. This is 2.659 squared multiplied by 0.4. This is going to give 2.827 meter per second square. Now, if we want to know the magnitude of the total acceleration, then this is equal to 0.3 squared plus 2.827 squared under the square root, which is going to be 2.84 meter per second squared. So to summarize, we have discussed the three types of rigid body motion: the translation, the rotation about fixed axis. We still haven't talked about the general plane motion. So as I said, we discussed the rotation about fixed axis, and we also discussed the constant angular acceleration relations. We talked about gears, and we defined the meaning of rigid body. Thank you.